All right, welcome to our second last lesson on modern physics, number 10, quantum information. It actually won't be our second last video. I am going to throw in another video explaining quantum cryptography for our activity that we're going to do after this lesson. And our particle physics lesson I am going to split up into two videos, so we still have some more to go yet. So, quantum entanglement. Let's talk about entanglement. Oh, I just lost. There we go. Nope, it's not working. There we go. So, quantum entanglement means a correlation between particles stronger than any possible classical correlation. Whoa, what does that mean? What's correlation? Some of you might remember if you took, I believe it's that data management, where you talk about the difference between correlation and causation. Causation is the action of actually causing something, where correlation means if you measure one system, you can infer the other. So the example I have here, if it rains, is the sidewalk wet? Well, if you measure the fact that it rains, then you can infer the sidewalk is wet. But the sidewalk's not wet simply because you measured the rain. Okay, I also put another comic here I found hilarious. It says, I used to think correlation implied causation. Then I took a statistics class. Now I don't. Sounds like the class helped. Well, maybe. It's funny because he's saying maybe because he doesn't know if the class caused him to understand it or if it was just a correlation. Okay, you missed my jokes, I know. That's not actually my joke though. Here's another example. Imagine I have two boxes. Okay, and then I have a pair of gloves. I take one glove and put it in one box and the other glove and put it in the other box. But you don't know which glove is in which box. Now if I open one box and show you in this box is the glove for the right hand, then you can infer that the other box has the glove for the left hand. However, just the fact that you measured this box doesn't mean you caused that one to be the left hand glove. It was always there and it was always the left hand glove. You didn't cause that simply by measuring it. Okay, you simply inferred it. So classically, in this example, the gloves are well defined. What do I mean they're well defined? I mean, I said we had two gloves, one's right-handed, one's left-handed. Okay, but they were unknown. You didn't know which one was in which box. Okay, so that's a classical correlation. But in quantum correlation, not only are the states unknown, but they're also undefined. So what do I mean by that? Let's go out of the glove example and let's move into polarization. So let's do a classical example here. Let's say I take two photons and I polarize them in the same state. So I'm defining their state. And I say they're either going to be both horizontally polarized or they're both vertically polarized. And what we're going to do is we're going to take one photon and measure it in the HV basis. So when we measure it in the HV basis, if the photon's horizontal, it'll either 100% come through the polarizer or 100% not come through the polarizer. So we can clearly say, for example, this photon's horizontally polarized, so the other one must be horizontally polarized. Okay, so this is an example of correlation where the states are well defined. However, if we were to make a measurement in the 45 minus 45 degree basis, let me just call this diagonal and anti-diagonal. Well, when the first photon comes through our polarizing filter, and we ask it the question, are you diagonal or anti-diagonal? And it's going to say, both. So since it's a photon, a single photon, that means it has a probability, a 50% probability of passing through that polarizer and a 50% probability of being measured, say, diagonally polarized. Well, now you can't make any inference about the other photon. You might say the other photon's also diagonally polarized, but then when you make the measurement, there's only a 50% chance that it will be. And so we don't have any correlation here. Let's look at this in a quantum system. So we're going to prepare two photons, same thing, but instead of doing them either horizontal or both or vertical, we're going to make them both. We're going to put them in a state of superposition. So these photons are both horizontally and vertically polarized. Now, if you make a measurement in the HV basis, again, similar to the classical state, right? It's 100% chance going to be one or the other. And so we have a correlation here. The interesting thing is when we make a measurement in the diagonal or anti-diagonal basis, or the 45 minus 45. So we can rewrite horizontal as being diagonal, anti-diagonal. So that just means horizontal is going to be diagonal plus anti-diagonal. And vertical is going to be diagonal minus anti-diagonal. And so I'm just writing that there as H is D and A and V is D and minus A. But just like when we do a superposition of states, right, I can say that horizontal here, our horizontal state, is this state plus that state, right? So the main thing is you'll have a diagonal state plus an anti-diagonal state, right, with some superposition there. So what I'm doing is I'm rewriting H as D plus A and as a plus for a superposition, and V as D minus A. Then you can do some simple math, right? You can expand, simplify, collect like terms, and what you get is DD plus AA. What that means is if you measure something in a different basis, these photons will still have a correlation. And so a quantum correlation is so much stronger than a classical correlation because the system itself can be undefined and they will still be correlated. Okay? Now, shortness cat we've talked about before, and it's a great example of superposition, but it's also a great example of entanglement. So we talked about the cat being in the box being both dead and alive, but the cat's state is entangled to the vial of poison state. If the vial of poison is broken, the cat's dead. If it's not broken, the cat's alive. Right? Those two states are entangled. Similarly, they're entangled to the state of the radioactive particle. If the radioactive particle decayed, well then the vial is broken. And if the vial is broken, the cat's dead. All of those states are entangled. Okay, so this is what entanglement means. And we can use this and lots of other quantum properties to make a quantum computer, which is what something places all around the world are doing. Right? And there's a big quantum computer at the University of Waterloo. That's pretty cool. So what is a quantum computer? Well, all computers are technically quantum, at least a little bit. And they have something in them called a transistor. Right? But those transistors are becoming smaller and smaller and smaller. It's called Moore's law. You might have heard of it. Right? Whereas computers are becoming faster and faster and faster. And they're becoming faster and faster and faster because we're able to make transistors smaller and so much more of them. Okay, so, but eventually, right, those transistors are going to become so small, suddenly they themselves are going to have to follow quantum rules. Right? Meaning if you make a measurement on them, right, they can change. And that's going to be really weird. But it's also a great opportunity. Why is it a great opportunity? Think of it like this. Let's go over how a computer actually thinks. A computer thinks in zeros and ones, called binary, or bits. Right? Any piece of information can be either 0 or a 1. And so what a computer does when you ask it to perform a calculation or you ask you to play a video on YouTube, all it does is choose 0 or 1, 0 or 1, 0 or 1, over and over and over and over again. Right? Computers from the 1950s do the same thing as your phone right now. The only difference is your phone can choose 0 or 1 a lot faster. That's the only difference. Okay, Well, what about if this 0 and 1 was a quantum state, and instead of saying 0 or 1, we put it in a superposition and said 0 and 1. And then if you actually disturb the state and make a measurement, then it becomes 0 or 1. But while it's in a superposition state, right, we can actually get a lot of cool things to happen. So how is this going to work? Right? What exactly are you going to put in superposition? Like an electrical circuit? Too big. Okay, so we can use photons. Right? We can place a photon in a state of superposition and make measurements on it. We can take, say, an electron and measure its spin, and a spin can be in a state of superposition. Right? So, for example, we could say for a photon, we say horizontal polarized photon is 0 and vertical is 1. We can say up spin is 0, down spin is 1. Right? And we can give these states a value of 0 or 1. Right? We can even take energy levels of atoms and give it a state of 0 or 1. And now we can entangle them. Meaning you can take one object, entangle it to another, and entangle to another. So let's say you have a computer, and it chooses 0 or 1, 0 or 1, 0 or 1 3 times. Now you have 3 pieces of information. But a quantum computer puts them all in superposition, and all of them are entangled. And so what are all the different possibilities you can have? They're all here. This is 1, 2, 3, 4, 5, 6, 7, 8, or 2 to the power of 3 possibilities. So whereas a classical computer has 3 pieces of information, a quantum computer has 8. This is an exponential growth. Imagine a classical computer had 20 pieces of information. A quantum computer would have 2 to the power of 20 pieces of information. What about 100 or 1,000 or 1,000,000? 2 to the power of 1,000,000 pieces of information? You can see why everybody's racing to build a quantum computer now, can't you? All right, so what can you do with a quantum computer then that a classical computer can't? Well, you can simulate quantum systems. And that can be useful in every field of science. You have a certain molecule, you want to know exactly how it's going to interact with something. Well, that's a quantum system. It's hard to simulate with a classical computer, but a quantum system could simulate that system. Right? And this can be used in fields of medicine instead of giving someone medicine based on, well, take 2 of these pills because your age is between these 2 ages. Right? A quantum system can accurately predict exactly what that specific individual should take. That's amazing. Right? And it can do it like that. You could make a really fast search engine. And you can factor really big numbers. And this is what I'm going to get into more on the next activity. But how does encryption work? Like when you go and you do like online banking that has 128-bit encryption. Basically, it's a factoring problem. Right? But I'll talk to you more about that factoring problem in tomorrow's lesson on quantum cryptography. Okay, but basically, it's a factoring problem no classical computer can solve, which is why the encryption is so great. But a quantum computer, solve it like that. Again, now you can see why businesses are also very interested in quantum computers. All right, this is a lot to take in, and I am going to post a couple other videos as well, which I think are also helpful to understand the idea of entanglement. Well, we've talked about a lot of quantum ideas. We've talked about superposition, we've talked about entanglement, and measurement disturbance, so I thought let's just relax and play a little game. Everyone know Tic Tac Toe? If not, you're going to watch me play a game. And I'm adding some rules to it. New rules, quantum rules. And after you kind of start to understand the rules, play it with your sibling, a parent, and quantum tic-tac-toe. Here we go. First player decides to make a move. Well, you can go in the top left corner and in the bottom right. Why not? That's superposition. That's our first move. It's one move, it's not 2. Right? because I'm only in one spot. You just don't know which spot I'm in. And I have a probability of being in one of those two spots. So I'm not cheating here. All right. Player 2 decides to move. And player 2 says, I'm going to go here. What did player 2 just do? Yes, player 2 made a move just like player 1 did in a state of superposition. But also look at the top left corner. Player 2 just entangled those two moves. Meaning, if we look over here, where's my mouse? If we look over here, these two states are entangled, meaning if you know what one is, you can infer the other. So if one actually exists here and not here, that means 2 must be here. But if one actually exists here and not here, that means 2 is here. So these two states are entangled. Yes, it's getting more exciting. So we got lots of different games going, and at the side you can see the different possibilities that can unravel in this game of tic-tac-toe. Getting more confusing? Player 1. What did player 1 just do? Player 1 made a measurement on their first move, right? And making a measurement collapsed the system. That's measurement disturbance. Right? Now you know that 1 is either here or here, and therefore 3 is in the other place. And because they're there, due to entanglement, 2 is here. So we just collapse the whole system, and this is what the game now looks like. And it may look, oh, red's going to win, right? But again, don't forget about your quantum rules. Lots of random things can happen. So as we continue to play the game, using those 3 rules, green just won. Okay, quantum tic-tac-toe. Try it with your friends online or your family. Okay, so hopefully everyone's okay with that lesson. On the back of your page, there is something called a simple quantum algorithm, and I made a separate video for this, and in order to understand it, you need to understand the Mach-Zehnder interferometer. So if you haven't done that yet, don't watch the next video until you have, or else it'll be quite complicated. Okay, but if you're interested to see really the true power of a quantum algorithm over a classical one, check out that video. All right. Have a good day.